Okay, greetings math people. Today we're going to be looking at a trapezoidal sum, or utilizing the trapezoidal rule. The trapezoidal rule is an improvement on the Riemann sum, basically improvement on the left and right Riemann sum. And today we'll learn how to use the trapezoidal rule and why it is an improvement to the left and right Riemann sum. So let's get right into it.
Specialize in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.
Okay, before we get into the trapezoidal rule itself, let's review a little bit stuff we did with the Riemann sum. So I'm going to utilize the same function I've used in a few of these videos on Riemann sums. And the function is where f of x is 18 minus x squared. And so that's the base function. And I want to review what we did. We did a left and a right Riemann sum. We were finding the area under this curve from 1 before in previous videos. So I'm just going to write the interval I'm looking to find the area from is from 1 to 4. And we'll briefly go back over what it was with a left Riemann sum, what it was with a right Riemann sum. Bear in mind the actual area under this curve is 33. So just keep in mind that the actual area under this particular curve was 33. So let's revisit the Riemann sums first. So let me do a sketch of this particular function. All right, so let's draw a little graph of this function. There's a little graph there. And so the graph is the downward facing parabola with a y-intercept at 18 and the x-intercept at the square root of 18, which is, a little more than 4. So this drawing isn't to scale. And so let's make some lines of demarcation here. So 1, 2, 3, 4, and then the square root of 18. And this, of course, up here is 18. So what I'm going to do is I'm going to find it a Riemann sum. And when I do the trapezoidal rule, I'm going to use 3 subintervals. So we're going to use 3 subintervals to find this. And, a particular important value for the Riemann sums is delta x. And that's an important value for the trapezoidal rule, the trapezoidal sum as well. And so delta x, just to remind you, delta x is b minus a over n, where a and b are the coordinates of the beginning and the ending of the interval in which we're finding the area of, and n is the number of subintervals or the number of rectangles or the number of trapezoids. So in this particular case, delta x is 4 minus 1 over 3, which equals 1. All right, so delta x in terms of a Riemann sum, if we're using rectangles, it just represents the width of each particular rectangle. So we start at 1, and then I add delta x until I get to b. So I start at a, I shouldn't say I start at 1. We start at a and we just keep adding delta x until we get to b, and that gives us the numbers of our subintervals. So we go from 1 to 2 to 3 to 4. So those are the numbers of our subintervals. So those are 4 numbers that represent 4 subintervals. Those are 4 numbers that represent 3 subintervals. The subintervals being from 1 to 2, 2 to 3, 3 to 4. Now, let's say we find a right Riemann sum for this particular case. So what happens on each particular subinterval, so this first subinterval right here from 1 to 2, so I'm going to draw a rectangle on this subinterval from 1 to 2, but I'm going to hit the function on the right end of the rectangle. The rectangle has a left end at 1 and a right end at 2 for this particular subinterval. I'm going to hit the function at each right endpoint, and that's why we call this a right Riemann sum. So I'll hit the right there I am. I'll go over to the other one. Next subinterval from 2 to 3, I'll hit it at 3 and then go over. Next subinterval from 3 to 4, I'll hit it at 4 and then go over. And so the problem with the Riemann sum with these rectangles is this open space. You know, that open space, that's area that I'm not getting. And so that makes this particular estimate, a Riemann sum is just an estimate of the area under the curve. It makes it a little inaccurate, you know, due to this open space. So basically what we have 3 rectangles. They all have widths of delta x, which in this case is 1, and their particular heights, since it's hitting the function at these endpoints, since it's hitting the function at 2 and at 3 and at 4, their heights are f of 2 and f of 3 and f of 4. So to find this area, we just take delta x, which is 1, times f of 1 plus, not f of 1, I'm sorry, f of 2. I was thinking of a left Riemann sum. Please forgive me. Let's get rid of that. And let's go back to the drawing board. All right, so my height, f of 1, my height 1 times f of 2 plus f of 3 plus f of 4. All right, and we're just plugging these values in to this function here. So for instance, f of 2, that's 18 minus 2 squared. That would be 14. And f of 3, that's 18 minus 3 squared. That's 18 minus 9, so that would be 9. And f of 4 is 18 minus 4 squared. It's 18 minus 16. That would be 2. And if we add that up, we get 25. Now, again, bear in mind that the actual area is 33, but we should have anticipated to get a number less than 33 because of this open space. So that's what we get for a right Riemann sum for this particular function with 3 subintervals finding the area from 1 to 4. Let's quickly look at the picture doing a left Riemann sum for this particular situation. So, you know, all of this information is going to be the same. Delta x is still the same. It's 1. The numbers of our subintervals are still the same, 1, 2, 3, and 4. What's going to change, of course, are going to be the heights of the rectangle. The width of the rectangle is still going to be delta x is still going to be 1, but the heights are going to be different. So let's take a look at this particular situation. So let's get rid of this junk. And let's also get rid of this junk here. And let's sketch a new graph of the particular function. All right, so just a quick new graph. So here's some Cartesian plane. And here's the graph of f of x, not to scale, of course. And so let's mark our numbers 1, 2, 3, 4. And this up here, of course, is 18. All right, so now we're going to hit the function with the left endpoint of each rectangle. So when I do this subinterval from 1 to 2, I'm going to hit it with the 1, the guy on the left, and then go, oh, I rounded that a little bit. Sorry. And when I hit the guy from 2 to 3, I'm going to hit it at 2, go over, come down. And then when I hit it from 3 to 4, I'm going to hit it at 3. And so little sloppy on the drawing there, but I think you get the picture. And so we can see here the problem with this particular estimate is it's going above the curve. So it's going to be an overestimate. It's going to give us a number which is greater than 33. And if we look at our heights, where we can find our heights, in this case, they'll be found at f of 1 and f of 2 and f of 3. So an interesting thing, when you get your numbers of your subintervals, if you're finding a left Riemann sum, you will evaluate the function at every value of the subintervals, every number of the subinterval, except for the last one. So to find your heights, you evaluate the function at every number of the subintervals except for the last one. And that should make sense. If I look at the subinterval from 1 to 2, and I'm going to use this number, the number on the left. Go to the next one, use this number, the number on the left. And go to the last one, I'm going to use this number, the number on the left. The last number will never be a number on the left, so it won't be used. And for a right Riemann sum, it's just the opposite. So a right Riemann sum, I'll start from 1 to 2, I'll use the 2. 2 to 3, I'll use the 3. 3 to 4, I'll use the 4. I'll never use the first number because the first number will never be the number on the right. So if you know the numbers of your subintervals, if you're finding a left Riemann sum, you'll use every number but the last. And if you're finding a right Riemann sum, you use every number but the first to calculate your heights. All right. So let's go ahead and find this area. Again, we're anticipating to get a number which is greater than 33. And so we have our delta x, which is 1, and that'll be 1 times f of 1 plus f of 2 plus f of 3. And f of 2 and f of 3 I already calculated earlier, but these are real simple things to calculate. So f of 1, and again, remember, I'm plugging the functions, the values into this particular function. So when I plug in 1, that's going to be 18 minus 1 squared. It's going to be 17. And these values we got before. So let's go ahead and go through it. So f of 1 is 17. F of 2 is 14. F of 3 is 9. And when you add all that good stuff up, you get 40. So for the left Riemann sum, we got 40. And just some brief commentary about when Riemann sums are overestimates or underestimates. You can clearly see this particular function is decreasing in the interval we're looking at from 1 to 4. The function is decreasing from 1 to 4. Well, when a function decreases, a left Riemann sum is an overestimate and a right Riemann sum is an underestimate when a function is decreasing. The reverse happens when a function is increasing. So if a function is increasing on the interval you're looking at, then a right Riemann sum is an overestimate and a left Riemann sum is an underestimate. So that's the whole Riemann sum picture. And so let's now take a look at a trapezoidal rule, which is an improvement, a refinement on the Riemann sum. Let's see why, and let's see how close the trapezoidal sum is to the actual area of 33. Again, using only 3 subintervals. And we've shown in videos before, our Riemann sum videos, the more subintervals we use, the better the estimate is going to be. Here we're using 3. It's a small number of subintervals. It makes for an easy calculation, but a very inaccurate estimate. But we'll see when we do the trapezoidal rule, it'll be surprisingly accurate, even with only 3 subintervals. So let's take a look. So let's erase some of this. Matter of fact, let's just clear this whole page. And let's revisit the problem at hand. So the given function, again, our go-to function for these estimates of the definite integral is 18 minus x squared. We are approximating the area from 1 to 4. And we're using 3 subintervals. So let's sketch the graph again. Didn't mean to zoom in. Let's put back a sketch of the graph. So there's our plane. And there's the graph of f of x. And again, this x-intercept right here is at the square root of 18, so it's a little more than 4. So 1, 2, 3, 4. Now, this is the deal on the trapezoidal rule. So the deal is, instead of using rectangles as we use for the Riemann sum, the decision was to use trapezoids. And the reason is obvious when you look at it from a graphical standpoint. So if you remember from the left and right Riemann sum, on the right Riemann sum, we had that open space. On the left Riemann sum, we had that part going over the curve. Well, look what happens when we use a trapezoid. When we use trapezoid, excuse me. So what's going to happen on this trapezoidal rule? So I'm actually going to hit on my first subinterval from 1 to 4. I'm going to hit the function at both points. I said 1 to 4. My first subinterval from 1 to 2. I'm actually going to hit the function at both points, 1 and 2. But instead of just drawing some horizontal line to make a rectangle, I'm going to draw a diagonal line to make a trapezoid. I apologize, it's a very sloppy diagonal line, but I'm doing the best I can. And again, the next subinterval from 2 to 3, both guys are hitting the curve and diagonal line. And the next subinterval from 3 to 4, both guys are hitting the curve and diagonal line. So you can see there, it's pretty clear. I know my drawing is slightly sloppy, so it may look like it's taking the whole area, but it's not taking the whole area because these are lines and the function is a curve. So the function isn't a straight line, but it's miraculous. It's astoundingly close to the actual area. I mean, my drawing isn't that bad. It's actually a fairly good depiction of how close this approximation is to the actual area. Now, understand what we have. We have 3 rectangles. Now, this distance here, again, this distance is delta x. But for a trapezoidal rule, for these trapezoids, that distance isn't the width of the trapezoid. That distance is actually the height of each trapezoid. And just to remind you, the formula for the area of a trapezoid. So I'm going to write it down here. So the area of a trapezoid is B1 plus B2 times the height divided by 2. So that's just the general area of a regular trapezoid, where B1 and B2 must be parallel to each other and the height must be perpendicular to those bases. B1 and B2 are bases. So if I look at this trapezoid, these two guys are my bases. They're parallel. And this guy right here is my height. So for the trapezoidal rule, delta x, he represents the height. So delta x represents the height of each trapezoid. And what we call the heights for the rectangles, like f of 1 here, f of 1 and f of 2 here, and f of 3 here, and f of 4 here. Those are actually the basis of the trapezoid. Like in the first subinterval from 1 to 2, the bases are f of 1 and f of 2. And then the next guy from 2 to 3, the bases are f of 2 and f of 3, and so on. So what it looks like, since the height is common to all these, I can just put it in front of the function similar to how I did for a Riemann sum. So what the area looks like, I'm going to put the height in front. I know it's 1, it doesn't change anything mathematically, but it's 1 because I'm doing a real simple example. Of course, delta x won't always be 1. So I'm going to pull the 1 out. Now, some of you may be thinking I can pull this 2 that's down here out as well. And I can, and I will, but I like to leave it in at first and then pull it out so you can see what happens, versus pulling it out and then it may not be obvious the ending result. So I like to leave it in first and then pull it out later. So this is the height. So this is the height that you see in the formula, delta x here in front. So all that's going to be left going to be doing is B1 plus B2 over 2. And so in this first subinterval, B1 and B2 are f of 1 and f of 2. So we'll have f of 1 plus f of 2 over 2 plus, now we're to this next trapezoid. Its bases are f of 2 and f of 3. So plus f of 2 plus f of 3 over 2. And then this last guy has basis of f of 3 and f of 4. So plus f of 3 plus f of 4 over 2. And so that's the area there. And so now I think that's obvious that this is how the area looks. So now I am going to pull this 2 out. And so what I'm going to have in front is a 1/2. And it won't always be a 1/2, but it will always be delta x over 2. So anytime I do a trapezoidal rule, I can pull out delta x over 2 in front. But in this case, delta x happens to be 1. So it's 1 over 2. And if you look at what I have left, I have an f of 1 plus, but look, I have an f of 2 and another f of 2. So 2 times f of 2 plus, look, I have f of 3 and another f of 3. So 2 times f of 3. And then plus, there's only one f of 4, so f of 4. And so if you think about, if I do any problem using the trapezoidal rule, if you think about it, the numbers other than a and b, so f of a and f of b, will be doubled because they'll appear twice. It'll appear in this trapezoid. So if I look at these bases, for every base other than the first and the last, for instance, f of 2 is a base for this trapezoid from 1 to 2. It's also a base for the trapezoid from 2 to 3. F of 3 is a base for the trapezoid from 2 to 3. It's also a base for the trapezoid from 3 to 4. So that will happen with every number except for the first and the last number. So for every number except for A and B. So when I do this trapezoidal rule, this trapezoidal sum, when I find the numbers of my subintervals, I will double f at those numbers at every value except for f of a and f of b. So this is what we have. So we have 1/2 plus f of 1 plus 2 times f of 2 plus 2 times f of 3 plus 2 times f of 4. So let's actually see what this comes to, what this value comes to. Again, remember the actual area is 33. When we did a right Riemann sum with 3 subintervals, we got 25. When we did a left Riemann sum with 3 subintervals, we got 40. Let's see how the picture plays out for this Riemann sum with 3 subintervals. Excuse me, with this trapezoidal sum with 3 subintervals. All right, so we've already kind of calculated these numbers of f of 1, f of 2, f of 3, and f of 4. So I'm going to go through their values very quickly. And so let's right up here. I have a lot on the screen, so let me just change the color to make this calculation stick out if we can. All right, so we have 1/2 times. All right, f of 1 is 17. It's 18 minus 1 squared plus 2 times. F of 2 is 14. And that's 18 minus 2 squared plus 2 times f of 3 is 9. That's 18 minus 3 squared plus, and f of 4 is 2. It's 18 minus 4 squared. And so this is 1/2 times. So this is 17 plus 28 plus 18 plus 2. So if we look at these two numbers are 20. This guy is 48. So 20 plus 28 is 48. And 48 and 17 is 65. So we have 1/2 of 65. And 1/2 of 65 is 32.5. Oops, that's It's not the best circling in the world. Actually, let's just do this. Let's try our hand at, I'm on eraser. Let's try our hand at circling again. And actually, let's just underline for simplicity. No, let's box. It's actually not the best boxing in the world. All right, you can see the answer. I'll underline. That's the answer there. So we can see we only use 3 subintervals, and the answer we got was extremely close to the actual area. And so that is the benefit of the trapezoidal sum. So again, just to recap the process of finding a trapezoidal sum when they give you a function. You find your delta x like you normally find your delta x, b minus a over n. You list the numbers of the subintervals, and so you start with a and you just keep adding delta x until you get to b. And we said for a left Riemann sum, we'll use all numbers but the last. We said for a right Riemann sum, we use all numbers but the first. Well, for a trapezoidal sum, we utilize all the numbers. But when we utilize those numbers for the basis of our rectangles, we will double all of the values between f of a and f of b. We won't double f of a and we won't double f of b, but we'll double every value between those for the basis. And it will always be multiplied by delta x over 2. And, because delta x is h and the 2 is just in the formula. So when we're multiplying the beginning by delta x over 2, it's coming from this part of the basic formula for the area of a trapezoid. And everything in here is coming from the b1 plus b2 is coming from the basis of the trapezoid. All right, last thing I want to look at is finding a trapezoidal sum when the function is given as a table versus just some function equation is given as a table. So let's take a look at that. All right, so here's the problem at hand. And so let me read the problem. So it says water is flowing into a tank at a rate r of t, where r of t is measured in gallons per minute and t is measured in minutes. The tank contains 11 gallons of water at time t equals 0. Values of r of t for selected values of t are given in the table below. Using a trapezoidal sum with the 3 subintervals indicated by the table, what is the approximation of the number of gallons of water in the tank at time t equals 0? Now, one thing to be very careful about, so we're going to find a trapezoidal sum for this particular situation, but we have to be mindful of the fact that there is already 11 gallons of water in the tank. So we have to be mindful of the fact that there's already 11 gallons of water in the tank. Because it wants us to approximate the number of gallons of water in the tank at time t equals 0. It's not asking us to approximate how much water flowed into the tank, which r of t represents. It's asking us to find just the number of gallons of water in the tank. So we have to take into consideration the amount that was already in the tank at time t equals 0. So when we find our trapezoidal sum, we're going to add 11 to that number. And for my AP calculus students, that's something you have to be very careful of, because a lot of times a problem like this will show up as multiple choice. And one of the answers will be the answer from the trapezoidal sum without adding the initial value, which in this case is 11. So be very careful. All right, so in essence, it's still the same formula. We're doing 3 different trapezoids. And the formula for those trapezoids is b1 plus b2 times the height divided by 2. The difference here is the heights are different. So when we were looking at a function, the heights were the same for each trapezoid. And again, the height was delta x. So I could factor that height out and I can just multiply all the bases times delta x over 2. Well, I can't do that here because all the heights are different. So I can't factor the heights out. But, the 2 that's in the formula, b1 plus b2 times the height over 2, that 2 in our denominator, that number is never going to change. So I can factor that out. So when I do these trapezoidal sums from a table, the first thing I'm going to do is factor out 1/2. So for these, it will always be 1/2. Now we're looking at a function. It won't always be 1/2. It will always be delta x over 2, which in the problem I just did happened to be equal 1/2 because delta x happened to equal 1. But of course, delta x is not always going to be 1. So when doing a function, you won't always take out 1 over 2. What you always take out is delta x over 2. But when doing a table, you will always take out 1 over 2. All right. So again, that just takes the 2 out from the formula. So we still have to do b1 plus b2 times the height. Now the heights will be determined by the independent variable. Remember when we were looking at the graph, the height came from x. Well, x correlates to the independent variable, which many times in a real life application will be time. So for instance, from this first subinterval, the height would be 2, because that's the difference of these two t values. The second subinterval, the height would be 4. And the third subinterval, the height would be 6, of course. And for our basis, again, we're just going to add the values of the dependent variable in each subinterval. So first we'll do 9 plus 5, and then we'll do 5 plus 7, and then we'll do 7 plus 8. And again, we're not going to do a deal where we just have a and then 2 times the next one and 2 times the next one and then f of b. And the reason we can't write it like that is, again, because our heights aren't the same. So let's go ahead and start it off. So again, our first height is 2. So this will be 2 times 9 plus 5. Our next height is 4. So plus 4 times 5 plus 7. And then our last height would be 6. So 6 times 7 plus 8. And again, we can see these numbers being used twice in the middle. 5 is there twice, 7 is there twice. But again, since these heights are different, we just have to write it out in this manner. All right, so let's see what we get here. So we have 1/2. And this is 2 times 14, that's 28. And this is 4 times 12, that's 48. Oops, I didn't mean to close that. And lastly, this is 6 times 15, that's 90. All right, so this one, so we have 2 options. We can sum these and half them, or we can half them and sum them. I'm going to half them and sum them. Anytime I have an option to do two different things, I tend to always do the thing that makes the number smaller first. Like if I'm doing a rational exponent where my numerator is the power and my denominator is the root, I'm going to take the root first and then the power second. So I like to make the numbers smaller when I have an option of doing 2 different things. All right, so I'm just going to half all these. So this would be 14 plus 24 plus 45. And let's see what we get here. We have 38 here, and 38 plus 45 is 83. So we have 83. However, remember there was 11 gallons at time t equals 0. So we have to remember to add that 11. And so the answer to the question is, I don't know why I tried to circle. So the answer to the question is 94. All right, that's going to conclude this introduction video on trapezoidal sums. Hope it was very informative and useful, and we will see you next time.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe-to-toe, impeccable, splitting your back, son, simple as addition and subtraction, black thought, the infinite relax one.